us look at a few common transformations in this lecture. Rigid transformation is a 4 by 4 matrix of this form. R is a rotation matrix, T is a translation vector, and this 0 bold transpose is a vector of zeros. So it's basically 0, 0, 0. The transform converts the column vector to a row vector, and 1 is just a single one value. This makes it a homogeneous representation of the transformation matrix. Rigid transformations preserve everything, that is angles, lengths, areas, and shapes. They are all preserved. Another transformation is a similarity transformation. The matrix of similarity transformation is similar to rigid transformation except for an additional scaling factor. Or we can also write it in this form so that S becomes S dash, where S and S dash are both not equal to 1, since if they are equal to 1 it will become a rigid transformation. Large S values over here enlarge the object. Small S values over here will diminish the object, and the opposite happens on this side with S dash. So because it's an inverse S value. Another type of transformation is the affine transformation, which is again a 4 by 4 matrix that has the form A, which is a 3 by 3 matrix and non-singular, a 3 by 3 non-singular matrix. T is again a translation vector similar to before. So affine transformations preserves parallelism, ratios of length, but it does not preserve angles. 0 is again a vector of zeros. Perspective transformation, the matrix can be a non-singular 4 by 4 matrix. Perspective transformation matrix preserves cross ratios. Cross ratios are basically ratios of ratios, and perspective transformation is what happens when you image something with a camera. Rigid transformation is equivalent to a change in coordinate frames. It has 6 degrees of freedom. 3 rotations, 3 translations, 1 each along the 3 axes. A similarity transformation has an additional degree of freedom, hence 7 degrees of freedom. The additional degree of freedom is scaling equally in all 3 dimensions. The affine transformation has 12 degrees of freedom. 3 rotations, 3 translations, 3 scaling, because it can scale objects differently along the X, Y, or Z dimensions. And it also has an additional 3 degrees of freedom of shear. It can put shear in objects. We will study a shear transformation in the next lecture. So the world and camera coordinate frames, when we work with representations, we work with n tuples or arrays of scalars. Changes in coordinate frame are then defined by 4 by 4 matrices. That is, a multiplication by a 4 by 4 matrix is equivalent to a change in coordinate frame. In OpenGL, the base frame that we start with is the world frame. Eventually, we represent entities in the camera frame by changing the world representation using the model view matrix. So remember this, you'll be using the model view matrix frequently in your code. Initially, these frames are all the same. That is, M is equal to I. The transformation is an identity matrix. When you multiply the identity matrix with anything, it does not change. So moving the camera, if objects are on both sides of z is equal to 0, we must move the camera coordinate frame. That is, we must translate the camera by -d so that it goes a distance d behind, so it can look at all the objects in front. A transformation maps points to other points and vectors to other vectors. There is basically a one-to-one correspondence between the mapping. So if we start with 5 points, we transform them, we end up with exactly 5 points, and the same goes for vectors. This slide shows a pipeline implementation of the transformation that we just studied. So we start with vertices. Vertices are transformed with the matrix T, and this gives us another set of vertices. The distance between these vertices may have changed depending upon what type of transformation we have applied, or it may not have changed. The rasterizer then completes the gap between the vertices. So we only need to be concerned about the endpoints while working out the transformations, and then it is up to the rasterizer to decide what to fill in the gaps. Let's look at some notations. We'll use uppercase PQR as points in an affine space. We'll use lowercase PQR as representation of points like their alpha or gamma values, which will be arrays of 4 scalars in homogeneous coordinates. We'll have a 0 at the end if this is a vector, and a 1 at the end if these are points. We'll use UVW to represent vectors in an affine space. Arrays of 4 scalars in homogeneous coordinates will define these vectors, and we'll use alpha, beta, and gamma for scalars. Translation is basically moving a point to another location. So a given point P displaced by D will move to P dash. Displacement determined by a vector D has 3 degrees of freedom because D can move P along the x-axis and the y-axis and the z-axis simultaneously. Hence it has 3 degrees of freedom. Although we can move a point to a new location in an infinite number of ways, when we move many points of a rigid object, there are usually only one way. So if we are going to have these points moved correspondingly to these points, there's only one way to move them, and the shortest way is this. Multiple translations when added up together will result in one translation, and it is up to us to decide whether we want to apply that translation simultaneously or step by step. For example, if you want to animate a person walking along a curved line, we might want to do a piecewise transformation. Translation using representations. Using the homogeneous coordinate representation in some frame such as p is equal to x y z 1, p dash is equal to x dash y dash z dash 1, and d is equal to dx dy dz 0. Note that this expression is in 4 dimensions and expresses point is equal to point plus vector. See, p dash is equal to p plus d, where p and p dash are points and d is a vector. So a vector gets added to a point, we get a point again, and this holds nicely because if we add d to p, this 1 and 0 will add up to give us 1 again, and hence the addition of a vector and a point gives us a point. And the specific x dash y dash z dash values can be calculated as x is equal to x dash is equal to x plus dx, which is the x component of the displacement vector, and the same goes for y and z. These are the y and z components of the displacement vector. A translation only matrix is simple to define. It's basically the rotation part is a identity matrix. This is always fixed to zeros, this is always 1, and we end up with only having our displacement vector values in the first 3 places of the last column vector, dx, dy, and dz. The x, y, and z displacement will always be placed like this. This form is better for implementation because all affine transformations can be expressed this way and multiple transformations can be concatenated together. We'll see concatenation later. But notice that whether we are doing rotation or translation or a combination of rotations and translations, we always use a 4x4 transformation matrix.